Chapter 2, Lesson 3, Newton's second law. How do forces change motion? Think about different ways that forces can change an object's motion. For example, how do forces change the motion of someone riding a bicycle? The forces of the person's feet on the pedals can cause the wheels of the bicycle to turn faster and the bicycle's speed to increase. The speed of a skater slowly sliding across the ice gradually decreases because of friction between the skates and the ice. Suppose you're pushing a wheelbarrow across a yard. You can change its speed by pushing with more or less force. You can change its direction by pushing it in the direction you want to move. Forces change an object's motion by changing its speed, its direction, or both its speed and its direction. Unbalanced forces and velocity. Velocity is speed in a certain direction. Only unbalanced forces change an object's velocity. A bicycle's speed will not increase unless the forces of the person's feet on the pedals is greater than friction that slows the wheels. A skater's speed will not decrease if the skater pushes back against the ice with a force greater than the friction against the skates. If someone pushes the wheelbarrow with the same force but in the opposite direction that you are pushing, the wheelbarrow's direction will not change. In the previous lesson, you will read about Newton's first law of motion. Balanced forces do not change an object's velocity. In this lesson, you will read about how unbalanced forces affect the velocity of an object. Unbalanced forces on an object at rest. An example of how unbalanced forces affect an object at rest is shown in figure 16. At first, the ball is not moving. The hand holds the ball up against the downward pull of gravity. Because the forces on the ball are balanced, the ball remains at rest. When the hand moves out of the way, the ball falls downward. You know that the forces on the ball are now unbalanced because the ball's motion changed. The ball moves in the direction of the net force. When unbalanced forces act on an object at rest, the object begins moving in the direction of the net force. Unbalanced forces of an object in motion. Unbalanced forces change the velocity of a moving object. Recall that one way to change an object's velocity is to change its speed. Speeding up if the net force acting on a moving object is in the direction that the object is moving. The object will speed up. For example, a net force acts on the sled in figure 17 because the net force is in the direction of motion. The sled's speed increases. Slowing down. Think about what happens if the direction of the net force of an object is opposite to the direction the object moves. The object slows down when the boy sliding on the sled in figure 17 pushes his foot against the snow. Friction acts in the direction opposite to his motion because the net force is in the direction opposite to the sled's motion. The sled's speed decreases. Changes in direction of motion. Another way that unbalanced forces can change an object's velocity is to change its direction. The ball in figure 18 moved at a constant velocity until it hit the rail of the billiard table. The force applied by the rail changed the ball's direction. Likewise, unbalanced forces change the direction of Earth's crust. Recall that the crust is broken into moving pieces called plates. The direction of one plate changes when another plate pushes against it with an unbalanced force. Unbalanced forces and acceleration. You have read how unbalanced forces can change an object's velocity by changing its speed in its direction, or both its speed and its direction. Another name for a change in velocity over time is acceleration. When the girl in figure 17 pushed the sled accelerated because its speed changed. When the billiard ball in figure 18 hit the side of the table, the ball accelerated because its direction changed. Unbalanced forces can make an object accelerate by changing its speed, its direction, or both. Newton's second law of motion. Isaac Newton also described the relationship between an object's acceleration, change in velocity over time, and the net force that acts on an object. According to Newton's second law of motion, the acceleration of an object is equal to the net force acting on an object divided by the object's mass. The direction of acceleration is the same as the direction of the net force. Newton's second law equation: acceleration in meters per second squared equals net force in newtons out of mass in kilograms. A equals F out of m. Notice that the equation for Newton's second law has SI units. Acceleration is expressed in meters per second squared, m out of second squared, mass out of second squared, mass in kilograms, and force in newtons. For this equation, it follows that a newton is the same as kilograms times meter per second squared. Circular motion. Newton's second law of motion describes the relationship between an object's change in velocity over time, or acceleration, and unbalanced forces acting on the object. You already read how this relationship applies to motion along a line. It also applies to circular motion. Circular motion is any motion in which an object is moving along a curved path. Centripetal force. This ball in figure 19 is in circular motion. The velocity arrows show that the ball has the tendency to move along a straight path. Inertia, not a force, causes this motion. The ball's path is curved because the string pulls the ball inward. In circular motion, a force that acts perpendicular to the direction of motion towards the center of the curve is centripetal force. The figure also shows that the ball accelerates in the direction of the centripetal force. The motion of satellites and planets. Another object that experiences with centripetal forces is a satellite. A satellite is any object in space that orbits a larger object like the ball in figure 19. A satellite tends to move along a straight path because of inertia. But just as the string pulls the ball inward, gravity pulls the satellite inward. Gravity is the centripetal force that keeps the satellite in orbit by changing its direction. The moon is a satellite of Earth. As shown in figure 19, Earth's gravity changes the motion's direction. Similarly, the sun's gravity changes to the direction of its satellites, including Earth.